the previous one, and it will be performed by Dr. Svitoslav Serkez.
Let me share my screen. Good. You see it?
Yes.
Nice. So thank you so much. Thank you, Danilo, for inviting me, and it's a pleasure and honor to get a talk at this conference. My name is Svitozar. I'm working at the European XFEL. Well, it's like a double European. Okay, double European XFEL laser, and it's located in Hamburg. I did my PhD here about 7 years ago, and somehow I got stuck. So I'm part of the FEL physics group, and I do research and development of FEL physics. So I'm more of a machine guy in this perspective, but I also do a lot of optics. So in this talk, I tried to condense everything that might be interesting to you, in particular to students, as I see lots of them in the auditor. So first of all, I would like to step back and give some overview. What actually are we talking about when we talk about FELs? So I would, as Vitaly pointed out, rightfully, FEL is not a laser per se. So it's called laser, but I think it's some kind of an inconsistency of formulation, because it doesn't behave like laser, strictly speaking, and it doesn't act as it doesn't operate like a laser either. It's more of a super advanced synchrotron. So probably you know about that exercise, that if you have electron beam, which is absolutely nicely smooth with all of the electrons equidistant, and it enters the undulator, it will not laze, simply because of symmetry conditions. And for each electron, there would be an electron operating in the opposite phase and radiating in the opposite phase. So there would be just no radiation. And as Vitaly said, that we do have radiation from undulator simply because of shock noise, irregularities of electron density. But one could put that to the other, so to say, extreme, and try to bunch all of the electrons together into one macro particle, which is very small compared to the pulse duration, wavelength. And that's not that easy to do, practically speaking. But what one could still do is to redistribute the electrons such that they are bunched or micro bunched together at with some intervals close to the wavelength. And that's exactly what one can realistically do. How can we do it? Well, we can do it fairly easily by just waiting and let radiation do that by ourselves, because we are lucky that there is some instability of electron and radiation interacting with each other. So radiation and electrons are generating some radiation field, and then they move in this radiation field, and every undulator period, radiation slips ahead by electrons by one wavelength, and they transfer energy or receive energy from this radiation. And there are some locations along the electron beam which consistently gain energy, and locations that consistently lose energy. So eventually you will start seeing them gaining energy and losing energy, and higher energy electrons overtake slower electrons in the magnetic field of undulator. And that's how you get this micro bunches, or that's an old term, I would call it nano or angstrom bunches nowadays, developing simply by itself. So overwhelming bulk of the undulators that we have in the FEL machines, and we have lots of them, tens of undulators, several meters each, are just to wait for this electron beam to bunch itself and radiate, and then to radiate proportionally to a squared number of electrons, not number of electrons in the bunch, like in synchrotrons. And that's actually what happens. So this in turn leads to this very characteristic time and frequency aspects of FEL radiation. Namely, we have spiky structure. That's because only very relatively small portion of the electrons can, so to say, talk to each other because of radiation slipping ahead of them along the undulator. So at some point, I'm a little bit simplifying here. At some point, you will see that there is some causality region in the electron beam, and that's actually our coherence length, so to say. Of course, when you have exponential growth, it's a little bit more difficult, but more or less that's the case. So we have lots of spikes, lots of micro pulses along the FEL pulse in time domain. Each of them has its own roughly coherence time. And if you do Fourier transform, or in other words, if you other ways, if you look at the spectrum, you will see very similar picture, and dimensions of these spikes in time and frequency domain are very much relevant to each other. Good. So let's come back to the real machine. This is our European XFEL that's located in Hamburg. Actually, it's between Hamburg and Schönefeld. It's crossing the border of two lands of Germany. You can take a virtual tour over here. You can scan the QR code if you have phones nearby. It's actually quite fun to have an impression walking through the FEL. It's more than 3 kilometers long. It accelerates electrons to the monstrous energy of realistically 16.5 giga-electron volt. That's why we need up to this point. So it's a quite a long acceleration, compression, acceleration, compression to suppress certain self-effects in the beam. And then it's being distributed into 3 user beam lines. Also, on top of that, we do have very particular trained structure. So we have lots of electron beams hitting, going through the machine, and then nothing for a while. And that happens with 10 Hertz. That's a legacy of the technology being developed actually for collider, not for FEL. But we are living with this technology, and we had to adapt. All of the detectors had to be adapted to this specific and very interesting time structure of pulses. So they are micro pulses in the train are separated by 220 nanoseconds, which may be beneficial or not so beneficial for some experiments. Of course, it can be reduced if necessary. And yeah, it's actually the collaboration of many institutes over the entire Europe, and it's multi-user facility. It's always booked. So this is an example of our operation schedule in 2024, when orange actually are the days in which data is being collected to users, because or in other words, photons are being delivered to users. And Mykola after me will tell you about FXC side of which is one of the instruments. But we also have some blue weeks, we call them blue weeks, to do some studies with the machine. And one of the studies, for instance, we got 17 millijoules, not micro, but millijoules of pulse energy in SASA3. So this is one of the records that we got, among others, with our facility. And 17 keV, we still managed to get 1 millijoule. And this week we will have study of 30 keV to finally diagnose what we get out of those, because it's not that trivial to diagnose pulse duration at very high pulse photon energies. Yeah, you can also find out much more about European XFEL by reading our annual reports about science case. So I will not dive too deep into that. And if you have much better information online that I can provide. So, but let's focus on special operation modes of European XFEL, which are probably the edge of what's capable of what's possible. And this is kind of review of the second generation methods that Vitaly was skimming through, and putting in some more graphical form, in which you can see frequency doubling, Edward Pratt proposal, Saldin proposal, Tanaka proposal, for instance. Yeah, it's inverse tapering, proposal by also Schneider, Staldenstein, Miller. So we tried, of course, to use some combination of those, but in the end, we made a little bit different approach, which is based on SASA3 expected performance, which is extremely high among other facilities. We can have with 16 GeV beam about 100 microjoules per femtosecond of power, and very small coherence time of 0.8 femtosecond, which is very good starting point, and that's actually our sweet spot to generate short pulses in our machine. Another thing which is very nice is that we can go to nonlinear compression, and we have long drift between accelerator end and as the beginning of the SASA3 instrument, which is kilometer order, and that allows us to have very nice, strong space charge induced chirp, which in turn, if we further increase compression, we can get up to 2% bandwidth, which is very unusual for FELs. And actually that is the manifestation of frequency chirp over the pulse. So head of the pulse has higher photon energy than the tail of the pulse. And then in the end, if we found one couple of quadruples, which if you move them a little bit, if you detune the current through them, you can change transverse and longitudinal dispersion in the beamline. So, and that allows you to further compress the beam and a little introduce angular dispersion to the photon. So that's how our tuning looks like. So, yeah, I'm sorry to put that much of an info, but yeah, that I couldn't have find a way to compress it and make it more visual for this talk. Anyway, long story short, we managed to get very short pulses, basically one single spike long, which by itself is less than 1 femtosecond, by just using nominal FEL beamline nominal performance and just tuning some knobs, which is kind of interesting. So that's how we imagine our electron beam goes through the undulator. So basically it's very much tilted, and in the photo structure of undulator, it just rotates such a way that only small portion, high current portion, stays on axis and continues to emit being amplified. So, and that's very much agrees with our simulations, which were done in Genesis. You could see that if you have no dispersion through the undulator, you have many spikes, which we were talking about also with Vitaly. And but once you start cranking up the dispersion, you see that you end up with single-ish spikes. So that's what we have. But on top of that, we are lucky because thanks to Finland Academy of Science, we got funding to introduce magnetic chicane in the middle of the undulator. What magnetic chicane is basically for dipoles that direct the electron beam a little bit to the right and back into the on axis. And what it does, it allows us to control the delay between to introduce delay to the electron beam with 10 to minus 4 precision or so, which is quite good when it comes to small delays. So namely, we really can delay the electron beam with the femtosecond order precision up to 1 picosecond. And once you look at this split undulator scheme, you can see that actually you can treat those as two independent FELs. FEL1, which starts from scratch, from short noise, and allows you to reach to generate some pulse, and another one after that. And you can change delay between the two for the electron beam, which in turn means delay between the two pulses, pulse 1 and pulse 2. You have two color, which one could do pump probe studies with. And yes, we have demonstrated way before nice stability and interplay between the two no interplay between two colors. And pulse energies are quite good also, up to 1 millijoule per pulse, which is really a lot when it comes to split undulator schemes. And we explore them up to 3 keVs almost. The thing is, one can combine both methods and have very short pulses for pump and probe. And that's actually what you see here. These are spectra, 10 consecutive events for very short pulses, single spike-ish, which should be below 1 femtosecond. And if one just picks some subset of them with equal intensities, one can see that spectra look very, very nice. And this is spectrum for one of the attosecond campaigns that we tried to measure. And if you assume, that's very important, you make an assumption that pulses are bandwidth limited and Fourier limited, let's put it this way, and you select events with only one spike and do Fourier transform, you can you can see the upper limit of your power and lower limit on your pulse duration. And then we got about 3-ish, 4-ish terawatt estimation on peak power, and consequently, conversely, about 200 attoseconds, below 100, around 150 attoseconds estimation on pulse duration. So we tried also to diagnose pulse duration with different methods. This is one of them. This is photon dressing measurement. So it will take a lot of time to explain it. So I would suggest you to look into this paper if you're interested. But the main idea is that you overlap FEL with optical pulse. So FEL kicks the photoelectron, and optical pulse adds a little bit of energy or subtracts a little bit of energy. Knowing the duration of optical pulse, you can see actually the length of this dressing, of this spoilage of photoelectron energy introduced by this optical light. And from that, you can deduce the duration of the pulse energy. But on top of that, that was much easier. Vitaly also mentioned about angular streaking. So we had this measurement and we ended up with 160 attoseconds or so pulse durations down to. This is the lower value, of course, quite optimistic. And pulse power, peak powers of about 1 terawatt, which is quite nice. Another special operation node, which might be interesting for you, is self-seeding. So what is this mode about? It's basically about removing this spiky structure of FEL radiation. So we do have this lot of spikes in time and frequency domain, and one can simply could potentially introduce radiation on top of electron beam, and it's called seed, and allow electron beam to amplify this radiation to saturation. And this radiation would impose equidistant microbunches without phase jumps. But the thing is, it's not easy to generate such a seed in hard X-ray range. So that's why we allow FEL to generate some light, monochromatize it, and then overlap this monochromatized light with the electron beam to allow it to seed itself in a way. And it uses wake monochromators, which are fascinating devices from the point of view of physics and optics by itself, because one needs to juggle a little bit with Fourier transform and realize and try to imagine how actually it works, because it's very counterintuitive. You to get a crystal, radiation hits the crystal, you reflect specific photon energy in the Bragg condition, and then nevertheless, despite that you're reflecting this energy, some monochromatic wake at this similar energy is actually following the pulse that passes through the crystal. We are talking about very thin diamond crystals. It's fascinating. It's nice. I love this concept. No time to discuss it though. But the thing is, this method allows European XFEL to generate extremely high spectral density. So here is the cross-calibrated spectrum to give you some absolute units. These are the millijoule per electron volt. So we got really 1 millijoule per electron volt per pulse. which is a record really for these schemes. And we do it twice to reduce the heat load on the diamonds, but that's very technical already. The thing about these diamonds is that you may not necessarily have only one break condition simultaneously. You may have several break conditions, and there is very nice line crossing within in diamond at around 7 keVs, where you have actually 5 lines, 004 reflection, and a family of 000 sisters and brothers. And by adjusting the angles, one could potentially see the seed, the self-seed FEL with several lines. So these are 1, 2, 3, 4, 5. But because of nonlinear effects at the end of the undulator, when you already saturate, you see emergence of other lines that actually indicate that you end up with a attosecond train, or the train of attosecond pulses. And that's actually also very interesting for us, was to demonstrate. We did it at PAL-FAL at Korea. So yeah, these are the trains of attosecond pulses of 600 attoseconds separated by 1.5 femtoseconds or so. And last but not least, but also to give you some impression what we are doing, we are not only driven by users, but also driven by our own curiosity. And after the invasion, we also tried to find some nice collaborations. And with Evgeny Bulak from Kharkiv, we came up with one scheme to study quantum electrodynamics at FEL, at X-ray FELs. So the idea was to basically back reflect the radiation that goes through the FEL, and then allow this X-ray radiation hit the electron beam. And because in this with these hits, lots of interesting stuff is going on inside the electrons because of interaction between electrons and photons, namely electron-positron pair generation by a few different processes like Trident process, Bright-Wheeler process, Compton backscattering. So lots of interesting and exciting stuff as well. So we are looking also a little bit beyond what users are asking for. Yeah, so also I would like to mention that in our group, R&D group, we are looking for interested students to do master students and PhD students. So if you're interested to collaborate, to learn something and bring this knowledge back, yeah, we are very much in favor. And please have a look at this website. Please write me or someone else in my group. Yeah, I encourage you. We will, for summer school, we will pay for getting to Hamburg and for accommodation and back. So yeah, and also for living costs. Yes, we have very big team that I would feel bad not mentioning, who made all of these studies possible. And I thank you so much for your attention.
Thank you very much for amazing talk. So basically very interesting development, and we have a question from Professor Luc Patet.
Hi, thank you for this very nice talk. I have a question. In the two-color experiments, can you actually swap the first and the second color in terms of short wavelengths? That means changing the high photon energy coming first or after the short, the longest wavelengths? And if yes, also what is the spectral separation you can get maximum to these two photons, two colors? For example, if you do that in a soft X-ray, can you reach oxygens and copper in the same shot?
Thanks, Luke, for a very nice question. So yeah, we did demonstrate first slice. So basically to put tail on axis first and then head on axis second. As I showed over here, we did it with Daniel at SUS. Oh, a little bit too much over here. With photon dressing, you see chicane off, one color arrives first, pump arrives before probe, and when chicane on, you switch their order and you can go further. The thing is that we don't have reliable electron diagnostics because at 17 GeV energy, I really don't want to put anything inside, and the streaking is extremely hard and extremely expensive. So we are talking about 5-7 millions just to measure this thing, right? It's not that easy to tune. So what also we proposed, and it's being implemented at the moment, is to split the central magnet of the chicane, introduce optical delay line to be more confident, to make sure that we smear out micro bunches fully, because this is one of the problems at small delays, to be able to deliver. When it comes to photon energy separation, of course, if it would be beneficial to generate lower photon energy second, right? Because you're less sensitive to crosstalk and stuff like that. However, still you're limited by the undulator K values, right, and gain. We can generate 2 pulses confidently, even up to 3 kV at high energies. But if we are talking about 3 kV and, for instance, 300 electron volt, that becomes tough, because it means that we need to go to 8 giga electron volt, and first pulse not easy, second pulse not that easy. So we now have extended second undulator with 4 Apple axes, as you know probably, and that adds us a little bit of magnetic length, so to the 8 meters extra, which helps a bit. But yes, it's not order of magnitude, so to say. Yeah, but that was nevertheless, users usually ask for neighboring colors, so close that I can see them with the on spectrometer simultaneously quite often, and yeah, it's not a big problem. Anyway, we are still working to improve.
So the user use it more to be on or off resonant rather than pumping to color or to absorption edge.
Yes, like below and above some edge, but different edges was one of the initial ideas of Michael Mayer.
Yeah, exactly. Yes. Okay. Thank you.
Like Leonard.
Thank you very much. Any other questions? I see there is no questions, so I would like to switch then to the